Welcome back. So far, we have used DC sources in every example. A battery sitting at a fixed voltage, but the wall outlet in your house gives you AC, alternating current, a sine wave that swings positive and negative, 60 times per second in some countries, 50 in others. Almost every piece of electronics, your phone charger, your laptop, your TV, needs DC inside to run. So somewhere in those devices, AC has to be converted into DC. That conversion process is called rectification, and the simplest version is what we cover today, the half-wave rectifier. Just one diode, one resistor, and an AC source. Let us see how it works. Here is the circuit. An AC voltage source on the left, a diode in series, and a load resistor on the right. We will start with an ideal diode, zero forward drop, perfect switch. The input voltage is a sine wave, Vi equals Vm times sine omega t, where Vm is the peak amplitude. On the positive half cycle, the input swings up to plus Vm. On the negative half cycle, it swings down to minus Vm. The diode is going to slice this sine wave in half. Let us see how. Look at the diode polarity in this circuit. The anode is connected to the AC source side, and the cathode connects to the resistor and back to the source. When the source goes positive, the anode is positive, forward bias. The ideal diode turns on, acts like a short circuit, and the entire input voltage drops across the resistor, Vo equals Vi. When the source swings negative, the anode is negative, reverse bias. The diode turns off, acts like an open circuit, and the resistor sees nothing, Vo equals 0. So the output is the input, but with all the negative humps chopped off. Just positive bumps with flat zeros in between. This is half-wave rectified. Now, what is the average value of this signal? If you integrate one positive hump over a full period and divide by the period, you get 1 over pi times Vm. And 1 over pi is approximately 0.318. So VDCC equals 0.318 times Vm. That is the DC component the load resistor sees on average. Memorize this number. It comes up everywhere in rectifier design. Now let us swap the ideal diode for a real silicon diode. Same circuit, same AC source, same resistor, only the diode model changes. Silicon does not turn on at 0 volts. It needs 0.7 volts of forward bias to start conducting. So during the positive half cycle, the diode does not conduct immediately when Vi goes positive. It waits until Vi reaches 0.7 volts. Only then does it turn on. And once it is on, it drops 0.7 volts across itself. So the output is Vi minus 0.7. This means two things change. First, the peak of the output is Vm minus 0.7, not Vm. Second, the diode conducts for slightly less than a full half cycle because it is off at the beginning and end of each positive hump. What about V_DC for the silicon case? The math gets a bit messier, but here is the practical engineering answer. When Vm is much larger than 0.7, we can approximate the output as a half-wave rectified version of Vi minus 0.7. That gives us V_DC approximately equals 0.318 times the quantity Vm minus 0.7. Let us put numbers on this. Say your AC peak is 10 volts. With an ideal diode, V_DC equals 0.318 times 10, which is 3.18 volts. With a silicon diode, V_DC equals 0.318 times 9.3, which is 2.96 volts. Not a huge difference at 10 volts, but at smaller signal levels, say 2 volts peak, the 700 millivolt drop becomes a much bigger fraction of your output. That is why low-voltage rectifiers sometimes use Schottky diodes with a much smaller drop, around 0.3 volts. Let us recap. A half-wave rectifier turns AC into pulsating DC by chopping off one half of every sine cycle. Just one diode, one resistor, one AC source. With an ideal diode, V_DC equals 0.318 times Vm, where 0.318 comes from 1 over pi. With a silicon diode, the peak shrinks by 0.7 volts, and V_DC drops to roughly 0.318 times Vm minus 0.7. The output is choppy, half the cycle is just 0. In real power supplies, we add a smoothing capacitor and use a full-wave rectifier instead, which captures both halves of the sine wave. That is exactly what we will build in the next lesson. See you there.